You ready? Yeah. All right.
A company is considering 7 investment options. Okay, let's say investment option I, where I be from 1 to 7. Then we know that if the company invests in project I, it will get a revenue equal to RI dollars. You can think of these investment projects, investment options like, I don't know, building residential buildings and renting them out. Okay? So we know the revenue if the company invests in project I. Also, we know the amount of money that we need to invest in project I. Okay? Each investment requires a cash flow at present in the amount of AI. Also, we know that the company has a budget limit, which is B dollars. Okay? Now, the objective is to formulate an integer program that maximizes the net present value of the investments. Okay? So technically, we want to select among these 7 projects, we want to select a set of projects that maximizes our revenue. Obviously here, what I want to do is to decide if I want to invest in project I or I don't want to invest in project I, right? So let me define my variables like this. For a project I define xy to be 1 if an investment is made on option I and 0 otherwise. So when I formulate my problem, I will get a 0, 1 values for my variables. And the variables that have a value 1 are those projects represent the projects that I want to invest on. Now let's formulate the problem. Of course, I want to maximize my revenue. So how should I represent my revenue based on these decision variables? If I invest in project 1, then I will get revenue R1. Okay, so if X1 is 1, this is the money that I will receive. If X1 is 0, then I will receive nothing, right? So this is the way that the revenue from project 1 based on my decision should be represented. The same is with project 2 and so on, right? So if x2 is 1, I will get revenue R2. If x2 is 0, I will get 0 from the second project. So let me write it in a more compact form. It is sigma I from 1 to 7 Ri xi. This is my revenue. Okay. What is my constraint? I cannot spend more than my budget. So again, if I invest in the first project, I will have to spend A1 dollars. If I invest in the second project, I will have to spend A2 dollars and so on. If the value of any of those variables is 0, then the corresponding spending is 0. Okay, so this function is my spending, which must be less than my budget, right? Everything works out. And finally, I have to specify that every variable is a binary variable. Then I'm done. Okay, a very simple formulation. Actually, this type of problem is a very famous problem, which is known as a knapsack problem, that every variable is a binary variable. You have a single constraint, and of course a linear objective function, and it has many applications, and it has been studied in many research works in the literature. Okay, the formulation is very simple. I think I will have this formulation in the next slide. Yes, as you see, every variable is defined as a binary variable, 1 if the investment is made an option, the corresponding option, and 0 otherwise. So I can formulate the problem like this. Okay, but the more interesting part of this problem comes next, when we want to add more restrictions on our investment capabilities. Okay, again, look at this. Simple form. Okay, in this formulation, the only constraint that I have is the budget constraint. So I cannot spend more than what I have. But what if, for some other reason, there are other constraints that I have to consider? For legal matters, for example, or some other considerations, I have to impose other constraints. I have to add other constraints to my problems. These are a few examples. So what if the company cannot invest in more than 2 options? Okay, how should we model this constraint, this limitation? If the company is free to invest in any number of projects depending on its budget, the formulation is already in hand. But here we have another constraint which says that you cannot invest in more than 2 options. Okay, so this is a very simple one. Simple means that x1 plus x2 plus x3, the summation of all my variables, must be less than or equal to. Only 2 of them, at most 2 of them, can take on a value 1. Okay, very simple. Now let's look at the other one. It says if the company, this is a new requirement. So when I have the first requirement, okay, in addition to my budget constraint, I just need to add this constraint to my formulation. Let's consider another one. If the company invests in option 2, they must also invest in option 1. Okay, what does it mean? It means that if option 2 selected, then option 1 must be selected. Or in mathematical terms, if x2 is 1, then x1 must be 1, 2. Right? So in other words, x2 must be less than or equal x1. x1 cannot be less than x2. Okay? So to make it clear, let's look at all possible options. x2, x1. 0, 0, 1, 1, 0, 1, 0, 1. Okay? Is it possible that have x2 equal to 0 and x1 equal to 0? Yes. It doesn't say anything about this. Actually, as long as x2 is 0, we don't care about the value of x1. But if x2 is 1, x1 must be 1 too. So this is not possible. And this is possible. Okay? Again, this simply means that the value of x2 is always less than or equal x1. Or So x2 must be less than or equal x1. So if x2 becomes 1, x1 has to be 1. Or we usually prefer to write it like this. So every variable is in the left-hand side. Okay? So done with this and done with this. Now let's look at the third one. Okay? Option 4 can be chosen only if option 3 is also chosen. Okay. The wording of this condition is a bit more complicated, but it actually is saying a very similar thing to the second constraint. Okay? The key is this only if part. Okay? Option 4 can be chosen only if option 3 is also chosen. It means that if you observe that option 4, pay attention, if you observe that option 4 has been selected, you can conclude that option 3 is also selected, right? Has the same meaning. So if you observe that option 4 has been selected, you can conclude that option 3 is also selected, because otherwise it is impossible. The condition says that option 4 can be chosen only if option 3 is chosen. Okay? Again, this is equal to say if I observe that x4 is 1, it implies x3 is 1 too. You see that it is very similar to the second condition, so I can write it like x4 less than or equal x3, or minus x3 plus x4 less than or equal 0. Now let's look at the last one. If the company invests in the second option, they cannot invest in option 4. Okay? If an investment is made on option 2, then they cannot invest in option 4. So again, let's consider the possibilities. x2, x4, 0, 0, 1, 1, 0, 1, 0, 1. Okay. Let's see which one of these conditions are possible, which one are not allowed. Okay? x2 and x4. If the company invests in option 2, they cannot invest in, since it says if the condition starts with investing in option 2, there will be no problem with no investment in option 2, so no consequence about option 4. Okay? How about this one? If the company invests in option 2, they cannot invest in, okay, it is very natural. If they invest in option 2, they cannot invest in option 4. So if x2 is 1, x4 must be 0, which is okay. How about the last possibility? An investment is made in option 2. Also, an investment is made in option 4. This is not possible, right? Because it clearly says that if you invest in option 2, you cannot invest in option 4. So what is the mathematical relation between x2 and x4 that represents the possibilities here? What this table tells us is that as long as x2 and x4, the summation of x2 and x4 is less than or equal 1, we are fine. The only violation happens when both of them take on a value 1. So this is the constraint that we have to incorporate into our formulation to cast this condition. Okay, I have the solution on the next slide. So, okay, here is the solution.